Whether my screen is visible?
Yes, sir.
Yeah. Okay, so welcome for today's class, and today's class is very crucial for the entire deep learning or neural network. You should say that because this entire neural network, basically the fundamental learning algorithm on which majority of them works is backpropagation algorithm. So we are going to derive this relation for this backpropagation algorithm from the scratch, or from the first principle, you can say that. And so here it's not a rigorous mathematics, but rather than rigorous substitution is there from here and there. So this backpropagation algorithm for which all we have been preparing from last 1 week or so, in terms of notation, in terms of concept, whether it's batch mode, online mode, or what we call sequential mode, etc. Finally, it will converge all those concepts into this particular algorithm. So before we start this, I want to just tell you that this algorithm works in two passes. One is called forward pass, another is called backward pass. So forward pass means when signal travels from the input to the output, that is the forward pass. And when the error propagates back from the output to the input level, that is called backward pass. You'll be surprised what do you mean by the output travels, the error travels from output to the input. So what I mean to say that when this error gets propagated back in due course of time, it keeps on changing the synaptic weights. And so during forward pass, no synaptic weight change happens. So whatever the synaptic weights are there, with that value you compute the output signal or the forward signals. Okay, so we'll see that. So of course in this there are two scenarios we'll be dealing with. Just to and whatever I'm going to talk about, the same can be generalized to a deep network as well. So we are going to talk about this neuron in a two scenario. The first scenario when our neuron under consideration is located at the output layer, and the another scenario where the neuron is located at the hidden layer. So I'll just take you to the board and just try to explain what I mean to say that when I say output layer and hidden layer, so that the analysis you can visualize this little better. So here what I mean to say, suppose you have some inputs here. Let's say these are this one and this finally. So I have to consider two scenario, and as of course we are assuming that they are all fully connected. So this is I'm considering is a neuron at the output layer. Okay, and these are hidden layers. So hidden layer 1, hidden layer 2. So two scenario we have to understand that if my neuron is available, the neuron I'm considering is available at the output layer, how do I change the synaptic weight when its signals get back propagated? At the same time, when any neuron which is somewhere in between the hidden layer, it could be any hidden layer, how do I change this? So two scenarios we are considering. The first scenario I'll be considering this scenario when the neuron is an output layer. And considering that, so you have this signal flow graph simply represented. So if you see here, so we notations are pretty clear. We have already said this. D is there. Desired value means corresponding to the training data input. The desired value is known to you, that is D. And when I say DJ, so J is the name of the neuron we am considering it, and that is the neuron J, and which is located at the output layer. EJ is nothing but the error produced by the neuron J. And of course, when I say N means the nth iteration or nth time instant. Yj is nothing but the output produced by this particular neuron, right? And you know that when I say minus multiplied with this, we know that when this particular as for signal flow graphs convention, when we mark this arrow means whatever is available here, and when it comes here, it is multiplied by -1. So here it will come minus time y of j, and d of j is coming. So you remember that as a signal flow graph, when two signals are approaching a particular point, they get sum. So it becomes dj minus y of j, which is nothing but e of j. Okay, and here if you see this, what is happening? Remember that all the biases we have fixed to one particular fixed input, that is +1, and that is so Bj can be considered Wj is 0, means the input is from nowhere, but we are fixing at +1. And rest is okay. We know that when with this jth unit and some input is coming from I, so wji, etc. And these are notation to show that there are multiple connections, multiple other neurons are there, and and imagine that this might have come from many previous layers. We are considering that this jth neuron is at the output layer. So with these things into mind, I'll start now this analysis. Is the scenario okay, clear for all of you? This is very crucial. That's why I wanted to emphasize more and more on this. So, oh, shall we move?
Yes, sir.
So once we have this, so as I mentioned this, the error signal as per this diagram on the previous page, E of j n is nothing but the difference between the two, d of j minus y of j, right? And the instantaneous value of the error energy, we know that at particular neuron j is nothing but half of Ej square n. This is straightforward, which we have been doing earlier. And the instantaneous value of the total energy. When I say total energy, means that in your output layer, it is not necessary that there is only one neuron. There can be more than one neuron also, right? So how do I find a total instantaneous energy over that time? So there is half, of course, and sum of this energy across all the neurons. So when I say this, literally what I mean to say is somewhere here. Let's say that at this point, output layer, there is one more neuron. So sum of energy of this neuron plus sum of energy of this neuron. So that's why it was basically mentioned like this. That is 1 by 2 and j in C Ej square n, where C is basically if it is A and B. So you say that C is nothing but A and B. There are two neurons in that. So you sum across the energy in the output layer. This is what it indicates. This will be further emphasized in next class when I solve a particular problem or deep learning, or particularly this forward in a neural network with the back propagation, either with the forward and backward, and then you'll be surprised, oh, my baby is learning, and then you'll say yes. And this I'll show with this only two examples going forward and backward, and that we'll see when I go for this. But before that, let me go for this generalization, and then we'll come to that. This, so this you understood what do you mean by C? It's the total number of neurons in the output layer. And we are assuming that the number of examples in a training set is some capital N. It could be anything. So the average squared energy for the entire training data you have is nothing but the energy of the network, and we are subjected to the entire training, that is 1 by n equal to 1 to n, and this one. This we have already seen when I was talking about the batch mode of training or batch mode of learning during last class. Now, so En and E average are function of all the free parameters. Can anyone of you tell me what do you mean by free parameters here? Hello, what are free parameters here? What I'm referring to?
They are expressed in independent variables.
What are those independent variables here?
The weight.
Yeah. So here free parameters is the only one thing, and that is the weights. So weights are the free parameters here. Good. Now we'll see this. So for a given training set T, E average represents basically the cost function as a measure of learning performance. That is the cost function. Some cost function you need to have it in order to proceed with further. Now the objective of learning process is to adjust the free parameters to minimize this error energy, right? So we have to find that value of synaptic weight, or basically that are the free parameters here, that will minimize this error energy. Theoretically, this value should be 0, means there should be no error, but that will be this is far from the reality. Something will be still there. So we want to find that value of W which will minimize this. So for this, we'll use an approximation similar to the derivation of LMS algorithm which we have seen, right? So that kind of approximation we are going to use. So we'll use sequential method, or what we call as an online method of training, in which the weights are updated pattern by pattern basis until one epoch. When I say one epoch, so suppose in your training data set is composing of 1,000 examples. So you have to go one by one till entire 1,000 examples get exhausted. Now subjecting the set of 1,000 examples to the network at a time is called one epoch. Now adjustment to the weights are made in accordance with the respective error computed for each pattern presented to the network, and that will see how it happens. So considering that particular example, we have to find the expression for the local induced field Vg, and because we have already subsumed this bias, so instead of starting I equal to 1, I can start from I equal to 0 if there are m number of attributes in my input space. What I mean to say here is, in this example, you keep into mind, this is m. Basically input is m dimensional. This is what it tends to say, and because bias you have incorporated, so I can say y is 0. So 0 is also indexed over there. So this is the reason. So wgin yi, and we just multiply and sum all those things. So this is my local induced local field. Now functional signal at the output of neuron J. So whatever comes here has to pass through the activation function. So activation function takes this local induced field Vjn and produces the output Yjn. So this is basically the output of neuron J. Once the output is there, so we'll see this. Now back propagation algorithm applies a correction, that is changes to the weights. Correction delta Wjin to the synaptic weight Wgi, which is proportional to dou V by dou Wgn. So this we already seen that this is basically depends on the process of what is called gradient descent. And gradient descent, we saw that change in synaptic weight, that is delta Wgi, is nothing but eta times this derivative, right? So this same thing here it is. So but now this part we are saying that E is depending on Wgi, W, but how it can happen, right? So how E can directly W this one, because we saw that E is immediately depending on E error E of J, so it is not directly depending on Wgi or W, and in turns we say that EI depending on yi. So how do I know all these things, man? So let's see this. So let me take you to the board, and I'll take you to the diagram also, so that it will be easy for you to visualize. Okay. So this is the diagram, and here I may go. So we say that, let me just write it this expression so that it's quite handy for you. So Vjn equal to summation I equal to 0 to m and Wjin yi of n. Okay, and then we are saying Vjn is nothing but phi j Vjn. This is the local induced field which we are giving to the activation function. Also, we know that Ejn equal to Djn minus Yjn. Okay, and also we know that E of n is nothing but 1 by 2 E j square n, right? So you see that this is how it is all related. Now we are saying that delta Wjin is directly proportional to delta Wji. Now if I see E, I cannot relate this W here directly, right? So I can see this, I can write it that, okay, as per chain rule is concerned, we can do this something like this in this fashion. E is depending on Ej. Ej is depending on Y. Y is depending on Vg. and Vj is depending on Wji. So much relation is going on. So this is very important that we write it across here. So I can say d of En over d of Ejn. And here I can say Ejn over d Yjn, and dou Yjn over Vjn, and then Vjn. From here I'm saying that Vj is depending on Wji. Is that okay? The chain rule now clear now? How do I know that I have to write like this? All these things are available here. Yes or no?
Yes. Yeah.
Yeah. Now let's compute it also. So suppose if I write Egn, what is the value I'm supposed to get right here? How much I should write?
Ejn.
Just Ejn, yes. And when I say here, how much I'm supposed to write?
-1.
-1, simple. Yjn over Vjn. So we don't know the nature of this function phi, so we'll write phi prime j, whatever is there, we'll see. Later we'll see what is the function of this. Okay. Now when I say Vjn over Wjin, what a value I'm supposed to get here? What value I'm going to get here? Tell me quickly.
Yin.
Hmm?
Yin.
Yes. Now many will have a doubt. Should I write summation here? But the summation should be there. Yes or no?
No, sir.
Yeah. So summation should not be there. The reason for this is very simple. Let me just write it across so that if so many people are there, if they have a doubt. If I write like this, Wji and I equal to say 1 to 3, so it will be Wj1 y1 plus Wj2 y2 plus Wj3 y3. And imagine that I have to say Vjn and I'm differentiating with respect to 2. So what I'm going to get it? Only Wj2, not anything else. So that's why here summation sign will not come into picture. Now all these things are there with you. You have everything with you. So all the 1, 2, 3, 4 substitution will do here. So we'll get it directly. We can get the value. I can just write it like it becomes minus Ejn and what is that? Ejny 5 prime jvjn and yin. All these things. Okay. So this is how it is going to be there. Now let's go back to this equation. Here we were. So we have found all this 1, 2, 3, 4, 4 components we found. And by substituting all those things, we got this relation straightforward, which we have seen that. Now, as for the delta rule, as I mentioned, this delta rule we have seen earlier in LMS, that is negation of uh, here we used to say nabla. So instead of nabla, I'm just writing this in partial derivative for the sake of ease, you can say that. And so we have this. So as per delta rule, so we can write it across. So I can write now delta Wji equal to this. So this when entire thing comes here, so this becomes basically plus, and I'm saying eta delta j yi. Now the question is, what is this delta, from where all this suddenly came? So this is basically called local gradient. This one is not the local gradient. It's the global means entire error energy you're considering. You are differentiating with that. Now imagine that locally there are multiple differentiation is going to happen with respect to the each neuron. So here, so this is called local gradient, which we denote by delta G and which is defined by dou E by dou Vj. So it is nothing confusing over there straight away. Of course, E directly is cannot be computed by Vj. We know that E depends on Ej and E depends on Y and Y depends on Vj. So all this computation you do further, and which is nothing but Ej 5 prime j Vj. So effectively same thing. Ultimately what I'm trying to say that instead of writing this part and this part everywhere, will be henceforth writing delta J. So that's why your change in synaptic weight becomes eta times delta J yi. So I can say that change in synaptic weight is directly proportional to the, if I take this a proportionality constant, which is nothing but the learning rate. So we can say that change in synaptic weight is directly proportional to the product of the local gradient for the jth neuron multiplied by the input to that particular neuron. Okay. Any doubts here? Hello. Do you have any doubt here? Okay. So this was the case. So we got the expression for how the synaptic weight will change will happen. Now, so just keep it. This is the case when the neuron is located at the output layer of the neural network. Now, what will happen if I consider a neuron from the hidden layer? So the scenario is quite different. So here we have to modify this backpropagation algorithm, or we have to develop, you can say that, for the when the neuron is a hidden layer. So far we are considering the neuron at the output layer, which we are calling is some neuron K. And for sake of simply again, the neuron we have considered as named as J, but now the neuron J belongs to the hidden layer. So hidden layer, you know that is not part of either output layer or the input layer, somewhere in between, right? Now the scenarios are quite different here. So we have to take it from here to this one, but notation slight changes because if the output neuron is named as K. So instead of J, we are calling it DK, EK, YK, 5K, etc. Okay. So this is what we'll be calling as. If you see that I have been calling as a 5J, etc. But here everywhere I'm taking 5. So we'll see whether it's feasible that a different neuron in the neural network will have a different activation function. There's a possibility, and yes, it is. But considering for the sake of simplicity and sake of computation, a mathematical convenience, we'll assume that all the activation function in the networks are the same. Okay. Now you consider this one. So let me say write it here across. So Vj is nothing but the sum of this one weighted inputs, that is Wj, etc. It will multiply all these things, and Yj is nothing but the phi of Vj, what is coming here, and those things will be given here. So here basically Vk's are nothing but again some of these inputs and some of this input multiplied by this synaptic weights, and then when it is passed, so Yk will be nothing but Vk, all those things, and here error will be nothing but Dk minus Yk. So everything remains same, but slight changes will happen here. And then we see, so local gradient for the hidden neuron J, as we know that local gradient is nothing but dou E by dou Vj, which we have seen earlier. but because E directly does not depends here, so here things will slightly change. Dou E by Yjn. So we'll see this, what will happen. So when I go for this, so dou E by, because if you see, E is available at here, Yj is available here. So directly you cannot jump from here to here. At least something should be here, right? So how do I go about this? So we'll see this relationship now. So dou E by, so we'll retain as it. Yjn, Vjn will retain as it is, and if this differentiation, so phi prime j Vjn. Okay, we'll write it. Now since En is, we have to consider this entire energy at the output layer, entire instantaneous energy at the output layer. So we see K is from C, and C is the number of neurons at the output layer, remember? And now, so on differentiating, when we differentiate this dou E by dou Yjn, dou Yjn, remember that we are differentiating with respect to Yj, so you can differentiate partially anything. So this will be 1 by 2, this is K, and this is basically 2ek, 1 by 2, so 2 will cancel, ek, and but ek is not depending on yj directly, so we still write dou ek by dou yj. So this is straightforward. Is there any doubt here? Any confusion? Hello? Is there any confusion here?
No, sir.
Okay. So now using chain rule, we wanted to know how do I do this. So remember that I have done something here. Because we have to establish relation between En, which is available at the output layer, and Yj, which is nothing but the output from the hidden layer. So how do I compute this? So for that, first of all, we have written this, what is instantaneous energy available at the output layer. And then we have differentiated with output at the output of the hidden layer, neuron from the hidden layer. So at output you have Ek, so we have written like this. So we are differentiating dou Ek by dou Yj. So we can rewrite as something like this. Now Ek is fine, but Ek is depending on Vk, and that it is, yes, I'll show you. Here Ek, that is the error, is depending on Vk via this phi, of course, and Vk is depending on Yj ultimately. So we can write something like this. So we want to compute this one, but for this we have to apply chain rule, that Ek is depending on Vk and Vk ultimately depends on Yj, right? So that you saw from the diagram as well. Now we'll proceed. So Ek, Vk, we can do this without any problem. So we have to write Ek, you know that is dk minus Yk. So instead of Yk, you can write phi of k Vkn, because phi is nothing but the output itself. Hence, when we differentiate this, it becomes minus phi prime k Vkn. Also, the local induced field for the neuron k is nothing but j equal to 0 to m, and wkj. Remember that earlier we used to sing ji, but we are talking about the local induced field at the neuron belonging to the output layer. So it is wkj. So neuron under consideration is k, not j, which is taking an input from the jth layer. So wkjn and yjn. So we have this vk. Now we can differentiate vk with wkj or yj very easily. So vk with respect to yj is nothing but the wkj. So substituting all those things in this thing, it got the value of this much. And we know that combination of ek and phi k, this one is nothing but delta k, delta, which we have seen earlier in the first scenario where the neuron belongs to the output layer, ek wkj, right? So once you have this, so you know now the story is simple. Finally, we know that the delta j, the overall, when you come back here, how do I get it? So when I delta j computation, when I do this, so delta j computation, we are using equation 1 and equation 8. So let's see what is this 8. We saw that local gradient of the hidden neuron is something like this. So this is already there. Entire thing that we have done so far is computing this part. So this part we have computed, and by substituting all these things, it becomes this negative goes 5 prime j vjn delta kn wkjn when the j is a hidden neuron. Now I can summarize this particular backpropagation algorithm in a simple way. So first of all, this is just a SFG for a part of a system pertaining to backpropagation of error signals. It says that how error is being propagated back. Now, so ultimately what you have is delta wji, which is nothing but learning rate multiplied by the local gradient into the input to that particular neuron from the previous layer, right? Yeah, you remember that it is from the previous layer. And where wj is EGN 5 prime J VJN if J is an output neuron. Remember that. However, if J is a hidden neuron, so this delta J value will be changing to this. So this completes the basically a BPA backpropagation algorithm. Now you may think that what this guy has coded so many equation and substitution is finally it boils down to what? How do I know this? If this making any effect or learning is happening? So hold on for some time. Probably next class, not probably, definitely I'll do this with a paper and pencil method. We'll take an architecture and I'll show you that it is what happening first of all. But before that, now let's see some of the part means what are this repercussion or this one and what are the condition, etc. We'll see. So now, because so far we have talked about this phi as a general, we don't know what this activation function is all about. We have not considered any particular activation function. So in my earlier classes, I talked about many activation functions, something called sigmoid, hyperbolic function, ReLU function, many version of the ReLU function. Here we are considering two for sake of mathematical convenience. One is, what if I'm taking a sigmoid function as an activation function? How my backpropagation algorithm changes, or I can write it. And what if I'm taking a tan hyperbolic function as activation function in that particular scenario, how my backpropagation algorithm looks like. So before that, we'll modify all these things. So we'll considering these two scenario. So let me consider the sigmoid function first. So sigmoid function is nothing but is a phi j vj, and it looks very complicated, but it is nothing. It is very straightforward. So sigmoid function, let's say if I'm saying phi of x, it is nothing but 1 plus e raised to minus ax or some scaling factor. This was only this much, and you know that we have already seen that how basically it looks like s kind of function is, right? So this a is nothing the steepness of this particular curve. Okay. So here I'm talking in reference to this notations which we have assumed. That's why it looks a bit complicated, but otherwise it's very simple. So phi j is my argument, which is nothing but the local induced field. It is 1 over e plus e exponential minus a vj, where a is some constant greater than 0, and vj can be any value from minus to infinity to plus infinity. Means it can be negative value or positive value, doesn't matter. It depends on the weights and the inputs. Now when I differentiate this with respect to vj, of course, we have to differentiate. This value comes out to be a exp over 1 plus exp, this one, right? And so this I'll do it now. So you'll get some idea. Suppose here this phi x is there, and if you people have forgotten this f by g rule, so do you remember? G f prime f g prime g square, right? So we remember this rule. So if I say phi x here, for this, how much it comes out to be? So g, so 1 plus e raised to minus ax, 0, differentiation of 1 is 0, minus f means 1, into differentiation of denominator, that is 0 minus a e to the power minus ax over 1 plus e to the power minus ax whole square, right? This part is anyway 0. So this is minus minus, this will become plus a e to the power minus ax over 1 plus e to the power minus ax whole square. Now the question is, how does it help me? So, and I'm trying to simplify the notation so that you won't get confused in the slides. So basically we are finding y here, which is nothing but it's some sort of phi of x we are denoting by y, because output of the activation is nothing but the y, right? Now once I have ax 1 plus is minus ax whole square, so I'll expand using by parts, So we are not integrating, but we have a particular objective to do so. We have done this in by parts in school in integral calculus. So ax plus b square, the rule, because this is there. If I take a LCM for this, so it is a times 1 plus it is minus ax plus b over 1 plus is minus ax whole square, and of course here everything is there. Now let me write what is happening here. A plus b constant terms together, a plus b and plus a times e minus ax, 1 plus e minus ax whole square. This and this denominator will go. What am this denominator component I'm comparing with this component. So this a plus b equal to 0 because there is no constant term here independent of e to minus ax. And another one is whatever the coefficient of e to minus ax is equal to a. So I can say that a equal to a. Ultimately I equal to minus. Now I'll substitute in this one. So when I substitute here, so this becomes a over 1 plus e is minus ax minus this is 1 over minus ax whole square. Now let's see what happens. They will say, what a big deal, man. So let's see what's a big deal. So if I say a, if I take constant 1 over 1 plus e is minus ax minus 1 over 1 plus e is minus ax whole square. Now, if I take this entire thing as a common, do you mind if I say 1 over minus ax, then it becomes 1 minus 1 over 1 plus e is minus ax, just only this much. Now, so what? Now, because y equal to phi of x equal to 1 over 1 plus minus ax, can I substitute this just by y of x or y of x? So here I can see a y of x 1 minus y of x. So then you'll say, so what's the big deal, man? So big deal is here. When we start writing those things in terms of simple thing, we can calculate all these things quite easily. So remember this entire derivation which I have done here. So here I have written directly. So but still I have wrote all those things. So this So ultimately you have written that phi prime is nothing but a yj n 1 minus yj. You just remember only this much. Now I hope things are clear by this time. Hello. Till now all is well. Hello.
Sir, I have a doubt in back propagation.
Tell me.
So, like in the part where we calculated the like the correction for the hidden layer. So
Mm-hmm.
in that case, the output will be going to many nodes, right? Like
Yes,
in
it
that
will.
particular layer, there will be many
Yeah,
nodes.
yeah,
So
yeah, yeah.
for which node are we calculating like the output? Like
Okay.
yn is for which node? Or is it
This
for
is
all of
that's
them?
yeah. That's what I'm telling. We started with this. See, we started here from the output, and finally we wanted a formula for a neuron which belongs to the hidden layer, right? Belongs to the hidden layer. So if you see here, when this one, in case of a neuron, when the neuron belongs to the output layer, your delta J, that is local gradient, is EGN times phi prime VJ on, only this much. But when we started all these things and we came across our delta J, that is the grade local gradient for the neuron which belongs to the hidden layer, which is nothing but phi prime J VJN, and it sums all the other thing which is belongs to higher layer. So just hold on, when I do this problem, it will be very clear. But this I have shown you at each and every step. But if you don't get it, just hold on. In next class, I'll take an architecture and solve it. Then you'll come to know how this really backpropagation happens in the different layer and other neuron also. Just hold on for some time. Anyway, so is this okay? Is this calculation okay? Clear? Of phi prime is becomes this value. Hello.
Yes, sir.
Okay. If this is okay, so we'll say now. Now for a neuron J as the output layer, Yj equal to Oj. So we are considering that if the neuron is taken from the output layer, so output layer, the output thing we are considering as a Yj. Yj is nothing but the Oj. This is the output value only. So the local gradient Ej phi j prime. This was the formula for a local gradient for a neuron at the output layer is. So Ej, we know that is nothing but Dj minus Oj. That is the desired output minus the actual output produced by the system. And A was the constant, right? So this is due to constant. This term is due to error, and this particular term is due to the phi prime j. That is yjn 1 minus yjn. Now it is just ojn 1 minus ojn. Only this much. So just you remember this. Now, same formula we are going to tweak it for the neuron which belongs to the hidden layer. So we know that for a arbitrary hidden neuron J, it could be belonging to any layer and any neuron. So just hold on, I can understand your confusion. Visualization is difficult till we work it out using paper and pencil. So this is phi j, and this is a definition, sorry, derivation which you already done. Phi prime vgn. So phi prime vgn, entire this thing you can write it here, but I cannot write ogn anymore. This is ygn. This is the output of that particular neuron, hidden neuron only. So ayj into 1 minus yj summation delta kn wkjn. How this delta kn will compute, that I'll show you. Don't worry about it. So this is all this delta k belong to the neuron from the higher layer. This is you are talking about the hidden layer, and means these values must be propagating from the other higher layer back to this neuron. Now this, it is not only it's basically it attains maximum value when it is 0.5 and its minimum value when it is 0 or 1. So this can be shown that for a sigmoid activation function, the synaptic weights are changed most for those neurons in the network where the function signals are there in the mid range, means around 50%, 0.5 or so. Now let me do this simple analysis directly to the hyperbolic function by I'm saying that now so far we have taken the activation function is a sigmoid function. Now what will happen when activation function I'm changing to a hyperbolic function? So basically the hyperbolic function is nothing but 10 hyperbolic. This one we take it where a b is some constant greater than 0, non-zero constant. So same thing we do. So here we are taking this prime, and we 10 hyperbolic. When you take differentiate, it becomes this AB, because B is a constant, so it's taken out. Secant hyperbolic square Vj. We know that secant square theta minus 10 square theta equal to 1. All these things are there. So by substituting all those things, we get here. Why we are substituting that? Because I want to write in terms of phi only. So that's why. So now this is 1 minus 10 hyperbolic square. So 1 minus 10 hyperbolic into 1 plus 10 hyperbolic. And now we know that phi j is nothing but yj. So we write here something. Now something has to be seen here. Because phi j when you write is a is a multiplier factor, but here a is missing. So it means I have to multiply a by here and here also, right? So basically when I take this multiplication, then the a will be there, and this will be a10 hyperbolic, so yj, and here a plus a10, so this one. So basically what is happening this, you are whatever you're multiplying, you have to divide it also. So you have to multiply it by a square, you have to divide by a square, right? So this one a will go here, another a will go here, a square when you divide, so this a will cancel, below only one a is left. So ultimately this phi j prime is something like this. This is prime value. So based on this, again you compute the local gradient value when the neuron is the output layer, where yj is nothing but oj, and again when your neuron is the hidden layer, then you compute with this. So I'll just stop here, and we'll see that in the next class, that with a particular architecture, how all this computation happens. I'll show you with the formula which we have derived for the tan hyperbolic function, all these things, and with the sigmoid function, and same idea applies to the tan hyperbolic function also. So I'll stop here. So another so go ahead here. So rate of learning, this we have already discussed the rate of learning, what happens. So basically BPA, which in short I'm calling for backpropagation algorithm, it provides an approximation to the trajectory in weight space computed by the method of steepest descent. So we are just approximating it, right? Because we don't know what is that. And we know when the value of eta is small, so smooth trajectory will be smooth, but learning will be slow. Means trajectory means it is moving towards the global minimum of error energy, so that you will get the weight space. And for large change, what will happen? Synaptic weights will assume such a form that network may become unstable. That is also there. And a simple method for increasing the rate of learning, yet avoiding the danger of instability, is to modify the delta rule. So this I'll discuss next class, because it's very important, and you now be in the mental setup that okay, time is ticking around. So we'll start here. So just be there a little. Let me take your attendance just to be there.